Here we're going to talk about the one of the big applications of probabilities, and this is what's called expected value. And expected value is the average gain or loss of an event if the procedure is repeated many times. This is actually something that insurance companies use a lot. What they'll do is they'll calculate expected values of insurance plans based on different risk factors, and risk factors are really just probabilities. For example, an 18-year-old male is more likely to be in a car accident than an 18-year-old female. And so they'll calculate what an expected value of an insurance plan to them would be based on those different risk factors. So we're going to learn how to do some basic examples like that. So we'll start with an example so you can just see it in action right off the bat, and then I'll give you the general formula. So in the casino game roulette, a wheel with 38 spaces, 18 are red, 18 are black, and 2 are green, is spun. In one possible bet, the player bets $1 on a single number. If that number is spun on the wheel, then they receive $36, their original $1 plus $35 more dollars. Otherwise, they lose their dollar. On average, how much money should a player expect to win or lose if they play this game repeatedly? In other words, what is the expected value of this game? So here's what we do. We do events. We write out our events, okay? And not just the events. We specifically will talk about the value of the events. So value of the events. And then next to that, we're going to do the probability of the event, okay? So in the game of roulette, there are really two things that can happen, okay? The player can either win or they can lose. So, and if you want, you can say win or lose, okay? And then we can talk about the values. So if a player wins, the value of playing the game was $35 because they ended up with a gain of $35. So this is 35, okay? If they lose, the value of the game is -1 because if they lose, they just lost the dollar, okay? So these are the two values of the two outcomes. Then we write the probabilities of those two. So the probability of winning, well, the person bets on a single number, okay? And then we spin the wheel. Now there are 38 different spaces. So the probability of winning is 1 out of 38, okay? And the probability of losing is, well, you lose with 37 of those spots. So 37 out of 38. So you start by creating a table that shows you the outcomes, the value of the outcomes, and then the probability of these outcomes. And then what we do is we multiply the value by the probability. So we're going to do 35 times 1 out of 38. And then we add, and then we do it with the next one, -1 times 37 out of 38. Okay. And then we just calculate what this is. And so this is, let's see, 35 minus a 37. So that's a -2 out of 38. And so this is, well, -2 out of 38. We're talking about money here, so I'm going to write that as a decimal. That's about -0.053 about. Okay, we're just rounding there to the nearest thousandth. This means that if a person plays roulette over and over and over and over and over and over again, we would expect in the long run, they'd walk away 5 cents poorer. So this process is the process we follow for expected values. What we end up doing is we take the value, okay, of an event, value of an event, okay, and we multiply by the probability of the event, okay, and then we add those all up. We add over all possible events. Do another one. You purchase a raffle ticket to help out a charity. The raffle ticket costs $5, and the charity is selling 2,000 tickets. One of them will be drawn, and the person holding the ticket will be given a prize worth $4,000. Compute the expected value for this raffle. All right, so this question actually is not stated very clearly, because when you're computing expected value, it should be expected value for one of the parties. So we're going to say that we're computing the expected value for you purchasing the ticket. Okay, so we've got our different events. Okay, and there are, again, just two events here. You can either win the raffle or you can lose the raffle. Okay, and then we'll do the value of E. So if you win the raffle, then, well, you paid $5, but you got a prize worth $4,000. So you came out $3,995 on top if you win. Okay. If you lose, you come out $5 in the hole. Okay. And then over here, we talk about the probability. Okay. So the probability of winning, there are 2,000 tickets that were sold and you purchased one of them. So the chances of you winning is 1 out of 2,000. The probability of you losing, of course, is the rest of them. So that's 1,999 out of 2,000. And so your expected value is, you take the value, 39.95, times the probability, 1 over 2,000, and then plus, do for the next one, -5, times the probability, 1,999 out of 2,000. And this comes out to be -3. So the expected value for you, meaning if you were to participate in a raffle such as this over and over and over and over again, in the long run, we would expect to lose on average $3 per raffle. Now, of course, this does not mean that when you are playing, you ever actually lose $3. Of course, that's not even a possibility. You either lose $5 or you gain $3,995. Okay, so expected value is not something that you actually expect to happen. It's the value, the overall value of such a game. Now, if we had done this from the point of view of the charity, these values would have been different. Okay. In fact, our events wouldn't really have been anything. There's really only one possibility, and that is, the one person wins. And so, from the 2,000 people that pay $5, you get $10,000, but then you give away a $4,000 prize. So for the charity, no matter what, this has an expected value of $6,000, and that is the only possible outcome for them. Let's do an example with insurance, because this is actually the most common application of expected value. So a 40-year-old man in the U.S. has a 0.242% risk of dying during the next year. An insurance company charges $275 for a life insurance policy that pays a $100,000 death benefit. What is the expected value for the person buying the insurance? So there are two possible events here, okay? The events are that the man lives, live the next year, or that he dies the next year, okay? And we want to know what is the value, for that person in each of those cases. So the value of each of those events. So if the man lives, then he paid $275 for nothing because he didn't die, and so no benefit was received. So it was a negative $275. Okay, and then if the man dies, then a $100,000 benefit is paid out. However, the man did pay $275. So we have to take the $100,000 and then subtract the $275. And so this ends up being worth $99,725. Okay. And then we look at the probabilities. Okay. The probability of living is, this is the probability of dying up here. And so it's just going to be, we're going to use the complement rule. Okay. And so the probability of living then is 1 minus this. So that would be 99%. So 0.99 0.99758. Okay. Notice this was written as a percentage, 0.242%, meaning as a decimal, this is 0.00242, which is here, 0.00242. So you'll notice that if you add these two together, you end up with a full 100%. Okay, which this column should always add up completely to 1. All right, so now for our expected value, we take our the value of the events, so negative 275, multiply by the probability, 0.99758, and then plus the 99,725, and multiply by the probability, 0.00242. And this comes out to be about negative 33. So what this means then is that the person paying for this life insurance, okay, expects that it's the long-term cost of such a policy would be about $33 for the year. So really what this means is, is the peace of mind of having a life insurance policy such as this worth $33? Because that's kind of what you expected, what the expected value is. What this also means is that for all the 40-year-old men that are paying for this insurance, this insurance company is expecting to make, on average, to make $33 per person. A friend offers to play a game in which you roll 3 standard 6-sided dice. If all the dice roll different values, you give him $1. If any 2 dice match values, you get $2. What is the expected value of this game, and would you play? So, let's talk about our different events. Okay, events. So, the events are, of course, that you either win or lose, and we're going to write that in terms of the rolling. So all the dice are different. So all different. And then the other one is that we have a match. Okay. All right. So now we're going to talk about the value of each of these. So if you roll all different values, then you lose $1 because you give them $1. So -1. However, if there's a match, then he's going to give you $2, and so you get $2. Okay. Now we need to know the probabilities of these. Okay. So we'd like to know what's the probability that all 3 dice are different. Okay. Well, probability. So there's 3 different die. So this is the probability that the first is different. First is different, and second is different, and the third is different. Okay, so this is an and statement, and of course the 3 dice do not affect each other, and so we could just multiply the 3. So this is going to be the probability that the first die is different. Now, and then times the third. Now, obviously, the first die could be anything you want it to be. Okay, no matter what, it's going to be unique. Okay, just the first die. So this is 1. Okay, it can be anything it's 1. In fact, I'll say, all right, there's 6 ways to roll something out of 6 ways to roll something. And then times, for the second die, you need it to be different. So there's only 5 possibilities there of what it could be out of the 6 rolls. And then for the third die, it can't match the first or the second, so there are only 4 possibilities for it to be different out of the 6. Okay, so this is 20 out of 36, or 5 out of 9. So all different. That's a 5/9 chance. And then the probability that they all match, or that there is a match, that's just the opposite of this. So we're going to use the complement rule. That's just 1 minus 5/9, which is 4/9. So for your expected value, we take our value, so -1, times the probability, and add those together for each of them. Okay, and so here we get -5/9 plus, and then this is 8/9. So this ends up as 3/9 or 1/3, okay, which is expected to be about 0.33. So 33 cents about is the expected value to you. Now, would you play this game? This is very important to understand how these things work, because even though the expected value is 33 cents, all this means is if you're going to play this game over and over and over and over again under the same conditions, that in the long run, you could expect to gain 33 cents. Well, first of all, if you were to do that, the question is it worth it to you to play this game over and over and over and over again to come out 33 cents ahead? Okay, I would say probably not. The other thing is, if you are not playing this game over and over and over again, this expected value doesn't really matter very much. What matters is the fact that the chance of you losing is higher than the chance of you winning. And so I would not play it, definitely not play it in that situation.